we built this category of relations. So yes, so sets and relations on them, where the morphisms are functions on the underlying set that respect the relations. And that's quite a lot of the way to having a category, but it's not all the way, because we don't have we don't insist that the relations are closed under identity and composition.
Right.
So categories are that stuff plus more. Correspondingly, it's straightforward to write a forgetful functor from categories to relations. That is forgetting that you've got identity and composition. And then the question was whether or not this functor had a left adjoint. So we built the mechanism to take any relation and close it under identity and composition by brute force.
By just little data type.
And that's this Kleene star thing, otherwise known as reflexive transitive closure, that just says, you know, we treat R as the edges and we build paths of finite length on top of those edges. And they're basically grown-up lists that have a bit more flexibility to them, or you can think of it as a bit of state. You could think of A as a set of states of some system, and R as the valid transitions of that system, and then these things represent a sequence of transitions of some sort. But they behave a hell of a lot like lists in all sorts of other respects. I mean, you can concatenate them, and the concatenation is associative and all of that stuff. And you can map stuff across them with exactly the relation preserving. You know, if you've got a function that maps one relation to another, then you can take transitions in one system and turn them into transitions in some image system. And that's exactly what we need to give us a functor the other way from any old relation to one that happens to be a category, because we've forced it to be a category by gluing identity and composition onto it.
Right.
So we're doing the previously on Buffy the Vampire Slayer bit. You haven't missed anything. And we were just at the point where we were going to come good on the claim that this thing is the left adjoint to the forgetful functor.
Okay, let's see if we can do that then. Let's have Agda tell us what we need to do. So we need to make these functions to and from the home sets, which is flipping a free category on the left to a forgetful category on the right, right? So let's see what we need. So here we are given something that is too small to see.
Yes.
We are given a functor from the free category, and we have to make a relation preserving function. Let's see if I can fix this up a little bit. So this x is on a insert mode. It's on R. Oh, now I don't have an equality symbol anymore. And I shouldn't have inserted these, sorry. Okay, let's say
yes.
B is as well. Okay, so we're given a functor f, which goes from the free category on this relation R into B, and we have to make a map from A into the objects of B, which preserves the relation.
Yes.
Right?
So,
so that's the map we want, and this is the functor we have. So let's see what this functor actually does. So what are the objects in this category? Just off the screen. Well, they are exactly A up there, right? So this functor on object takes an object in this category, which is A, and gives me an object in B, right? Which is exactly what I need. That looks good.
yes.
And now I need to show that this thing preserves the relation, right? So if A is related to B, then f of A needs to be related to f of B in this home category. But this is almost how we defined the morphisms in the free category, but this is just taking one step, right?
Yes. So in this direction, it's the traditional fabulous fact that we're allowed any number of steps, and 1 is a perfectly good number.
Let's see, why is it not
Yes.
happy about this? Oh, because I actually have to take the R first.
Yes. Yeah. But this
Right.
looks like
So I take a proof that A is related to B, that's my R, and then I want to produce something from f of A to f of B, and f map gives me things from f of something to f of something.
yeah, it looks like a good start.
And then here I just now have to consider how can I make something in the home, in the free category, which was defined to be the cleanest star of R, right?
Yes.
So this says I can take as many steps as I want, and in this case I want to take exactly one step and then stop, right? So I do R and stop. Then I was a bit confused, but it's going to be a star in something from something to something. Not quite sure what you mean. So the free category action on morphisms, it's turning. Yeah. But here I want to produce a particular element of star of R rather than star of R itself, right?
Yes.
Okay. And the other way, I am given some function, some proof that it's preserving the relation. And I have to make a functor from the free category into B, right? So I do that, saying what the action on object should be. So again, let me bring the X into scope. Call that B and R. Okay, so again, I need to go from A to object to B, but that's exactly what my function was. Right. I need to give an action on morphism, so that needs to take a star.
Right. So this says we can get from x1 to y. Terrible names. Okay, we can get from x to y in some number of steps. And we know how to turn each individual step into a morphism in B. We have to do the whole thing in one go.
Right.
But yeah, so what's the plan? Well, we know something about B, namely, it's a category. It's closed under identity and composition. So that's good news.
Yeah, right. So I think I would like to pattern match on how many steps we have here, right? because otherwise how can I apply this thing to get an individual R? And then I probably want to do a recursive call at some point,
Yes.
so I'm going to bring this out as a helper function.
I think that's
So I'm going to call that something like fold star. And in the end, I want to go from star x, y to on b f of x, f of y, and then I need to introduce all the things I have.
yeah.
So
Is this a job for Control C, Control H?
could be, but it's going to be really messy. But let's try it. Okay, so I want to give it f and p probably. Right, and this is what it tells me, unfortunately. So yeah, I think it's actually better to do it by hand.
Yeah, but see what Control U, Control U, Control C, Control H gives you.
Gives you the same thing. Okay, so if I do it by hand, so undo what I just did, I guess. Okay, so I can. So what do I have? I have some A, which is a set. I have R, which goes from A to set. I have that B is a category. I happen to know that I will refer to B later, so I'm going to make it explicit. I will probably start by doing it implicitly and then realize I needed it.
Yeah.
Okay, and then I have the F and
The F and the P.
To copy. And I have X and Y.
They can safely be left implicit.
Okay, and does it work? Gold star. Guess bring B into scope first. B, F, P. Okay.
Okay, fit for purpose.
B, F, P.
R's.
R's. Okay, and I said I did all of this because I wanted to pattern match on the R's, right? Because this is defined as a data type. So let's see.
So your, as ever, the type is 3 times as long, but nothing else is different.
I could, but
it's going to be a
in the
recursive
second
operation.
step here, I want to call myself again, so that's why I'm preemptively doing it the right way. Okay, so it's either 0 steps or it's 1 step plus more steps, right? If it's 0 steps, that means that x was actually equal to y, and we need to go from f of x to f of x, right? B is a category, amazing. So we can use the identity of B to go from one place to the same place. Otherwise, I suppose I should call this R. Okay, so now I need to go from f of x to f of y. I know that R takes me from x to b, and then I have some more steps that takes me from b to y. Right? So, and I also have p. So if I apply p to r, that's going to take me from f of x to f of b, right? Because r goes from x to b. So p of r. So that's starting in the right place, but it's not quite ending up in the right place yet, right? But then maybe we can take some more steps with the rest of the stars we have if we compose. Compose in B. The first thing I'm doing is P of R. So that's taking me from f of x to something. And now all I have to do is to go from f of b to f of y, but that's exactly what I do if I continue folding the rest of the steps.
Right, and the point is that, you know, the identity and composition structure that the category gives us is exactly the structure we need to be able to do this fold, and that's not an accident.
Yeah. If we didn't need the identity, for example, then this adjunction would not go through, right? So we're just identifying exactly the structure we need here. Okay, so now I need to prove that if I plug in the identity of the free category, then I get identity. But the identity of the free category was this thing, right? So the false star of this thing is identity, and the thing I had to prove is that ID equals ID. So that was okay. And then I need to show that this F map is preserving compositions, and composition in the free category was defined to be the append of the paths. So now I need to translate that to a composition. Right?
Yes.
And
So this is standard list-like business.
yeah, except our lists are now fancy.
Yes.
I wonder if I can get away with doing this inline. I'm going to try it, I think. Or not? Should we?
Oh yeah, I don't believe it. This is going to be induction on F1.
Yeah, let's try it. So F1, I'm going to call it H instead.
That's a wise choice.
I know I need to pattern match on this thing because this thing is defined by pattern matching on the H, right? Base case should be fine, I hope. Okay, so it's saying that something is equal to the composition of identity with the same thing, right? So now we see that we're also going to need all of the laws for. So I should have brought B into scope first. Pardon? I don't. No, but it's easier to just copy the whole thing. Because now here, right? So now I have B, so I can say identity. And never remember which one is which, so I'm going to try L first. That seems to be right. Where is it?
I always call these things id comp and comp id because then I can remember.
Right, so I named them the
Which one
same
is-
as in the standard library for other things, but yeah, so it's
Yes.
right if I only flip it with a sim. Okay, and here I have some R and some R's. And see that what we simply need now is that we have kind of the same thing in the right order, right?
Yeah.
Except that it's bracketed the wrong way. So now we need associativity of B and then probably something else.
Yes.
So maybe it's what is it? Okay, so now the first bit looks good.
Yeah, this is the quick and dirty style.
Yes, right. So you could also, just two things you could do. You could do equational reasoning, or you could use the solver to not do these things yourself, right? But I think it's small enough now that we can.
You now need a recursive gadget, and I think yes, okay, you can just about get away with doing it inline.
I think in this case it's going to be fine because
Yes.
this is just a proof referring to other things. I'm never going to refer to this proof again. So
Yes.
termination checker is clever enough to see.
Yeah, that's often the way that you need to farm out the operations, but you can do the proofs.
Okay.
Right.
Right.
and then-
So what have we done so far? We've defined the to and the from. One was easy. The other one we had to actually define a functor, so we had some proof goals there as well. But now we need to show that going there and back again is the same as doing nothing.
Yeah, and we're totally in the James Bond movie situation where if there's some gadget that we don't need by the end of the film, then the script's wrong.
Okay, so I'm just letting Agda tell me what I need to do. It said that for every functor f, I need to prove that from of 2 of that functor is the same as f. So I see that there's an equality of functors. So I'm going to use the gadget we have for proving equalities of functors. Okay, and then reassuringly, the first goal is easy. And for the second goal, it's not completely easy, right?
We can see we've got to pay for our cons nil somehow.
Right, so again, what can we possibly do here? So f map of f is actually, yes. So f map of s is a function, right? So I again want to show that these two functions are equal. And then I try to do it pointwise for every x, for every relation. Apply the left-hand side to x, that should be the same as the right-hand side applied to x. So here, I think it would probably be good to do a lemma. Do you think I can get away with it?
I doubt it.
Yeah. So I'm going to copy this. And again, because I'm not going to refer to this later, I can afford to do this locally. Maybe. Not directly, I think. But okay, so that's what I would like, but not everything is in scope. What is this? It's okay. I'm just going to bring everything into scope. Didn't like that. Okay. It's not in scope yet.
No, yeah, it's in the Ext.
Right. But here, it's annoying. Okay, I'm just going to do it by hand. So this doesn't make sense because these things are not in scope.
R is in scope, so it'll be able to figure out.
Ah, really?
Well, no, you'll need to universally quantify over them.
Ah, yes, exactly.
But it's not going to have any difficulty finding their types.
Yeah, right.
And you will want them to be locally universally quantified.
Right, because otherwise the induction hypothesis is not going to go through anyway. Okay, good. Dilemma fits. Some R's. Pattern match on the R's. See that what I need now is that F preserves identities, but I know that. Again, it's the wrong way around. Okay, so here I have an F map of a composition. So Tom Innovason. Is that right?
Right. You've got an induction hypothesis
Yeah,
that will turn your fold star into an F map.
Right.
And now you should be good to talk about.
Right. So now I can do homomorph F.
And you're going to need to do sim on that, but you're in the right sort of zone.
So this is talking about the comp of an F map and an F map. And is that enough? I'm just going to try and give it. And it is. So
That was lucky.
a little bit of magic.
Some,
But again, we see that what did we need? Exactly the fact that F was a functor preserving identities and composition, right? So using all of the structure we have. Okay, and here it looks a little bit scary. So this is an F and a P. We see that the first components are already the same. The second components are the same up to a composition with identity. So I think we are in a good place again.
yep, good start. And now we want.
Right, and now annoyingly, this is now inside of the R.
So let's go extensionality.
So let's go extensionality, and now we're going to hit another snag, which is that the type of the R was implicitly quantified over these A's and B's. So we need to actually use extensionality for the A's and B's as well. And there's a little gadget in the standard library which says that if you have extensionality for explicit function spaces, then you also have it for implicit ones. So let's copy that in here. Now we should be able to do it. Start with an IXed. So that's saying for every implicit X in A, that was the A that occurred in the R. And then we also have to do the same for the B. Amusingly, this IX are also taking the arguments implicitly, so you don't have to introduce them. And now we are in the place where we can talk about the R, do an X of the R. And now it's easy.
What do you know? Identity R has turned up.
ID B. Identity R indeed. Sorry. Identity. Right. So we used left before, so that means it has to be R now. Right. This time we don't even have to sim it. Right. So now we actually used all of the structure, right?
Have we?
Well, not quite. We haven't used.
Oh, no, we so far no, we're good, mostly.
Right.
Yeah.
So what have we used? We used associativity at some point. We used identity
Left
left.
identity,
and
right identity, and we've used both functor laws.
Yeah. So I think we used everything. So what is the then left to prove? If we have F and a G,
This is
we have to
looking.
show that this thing is equal to itself.
Thank goodness for that.
So again, proving naturality was not such a big deal.
I mean, it is often the case when you're working with these sets with structure sorts of things that naturality is not something you can mess up.
Yeah. Right. So, and then we can zoom out a little bit. So I think this is often a useful way to try to construct an adjunction, right? I mean, you think of something reasonable, then you ask Agda, what do I need to prove? And then you just get down in the trenches and do goal by goal. You don't really know what you're doing in a high level, but that gets you through the proof, and then you realize that you've done it, right? But of course, now we could think about what this actually means. So it's saying that functions out of the free category are in some sense easy to define, right? Because you don't need to deal with all the morphisms in the free category. It's enough to do it for just the generating morphisms, the individual steps of this star.
Yes. Right, and that's exactly, it's exactly the fact that you have to respect the identity and composition. That's to say that you have to respect the empty sequence of steps and the associative and the concatenation of paths. That means it's enough to consider one step at a time. There's no, you're not you can't do anything cleverer than consider one step at a time.
And the fact that we have these round trip properties also means that, in fact, every functor out of the free category comes from one of these, right? Because if I start with one, then I use the from or to or whichever one it is to turn it into just a function on the underlying relation, and then I use the other one to turn it back again and I get the same thing. So in fact, there are no other functors. They're all given by this simple fact in this case.
Right, and this often shows up in library design, not to put too fine a point on it, where what we're saying is that to get the structure respecting things, so the homomorphisms from the free, or the functors from the free category, right? So that's structure has to be respected. It's enough to do something boring in the category with less structure that works element by element. That's great, right?
And it's also good news for you, right? Because if you just define a functor on the free category directly, then you have a proof obligation to check that you preserved composition and identities, right? So you've done something, and then afterwards you have to do more work to check that it really was the right thing. Whereas if you construct it just on relations and then extend it to composition and identities, you know by construction that you've done the right thing, and you have fewer proof obligations. So it's better to not try to squeeze the toothpaste back into the tube after you think about. Okay, so we have a little bit more time. So pardon? What? Well, so an adjunction is a particular kind of natural isomorphism between homsets.
Yeah, this is the right place to go to in the remaining 15 minutes.
So let's now try and tie things together a little bit. So we talked about monads as things to do effectful things, and then we moved sideways to adjunctions because they are cool. But actually these things are connected in the sense that whenever you have an adjunction, then there's a canonical way to make a monad from this. And that is true the other way. So we're not going to go through this in the lectures, but in fact, every monad arises from an adjunction. But this is maybe the interesting end. So what's the idea? So I have these functors from C to D and from D to C, and I know that they have this adjunction property, which makes it possible for me to flip the F to the right in the homs, etc. And now I would like to make a monad on C. So what can I possibly do? Well, a monad on C is a functor from C to C, which has some extra structure and some extra properties, right? So I could try to make a functor on C. And what are the pieces I have? Well, I have a functor from C to D and one from D to C. So the only way I can think of make a functor on C, which is not too stupid, is to compose these things, right? I mean, I could also do the identity functor on C or something, but okay. And that would give a monad, because the identity functor is a monad, but it wouldn't use all the data I have, so that shouldn't be the right thing. So let me see if I can compose in the categories F and G. That's going to give me a functor from C to C. So I could do it the other way around, but then I will get a monad on D. And here I want a monad.
No, you would not get a monad on
right.
D. You'd get a co-monad on D.
I will get a functor on D. Yeah.
Yes.
Which would be a co-monad indeed. Because you can't swap the F and the G in an adjunction.
Yes. There's something about the left adjoint is always adding extra structure that you can't do without.
Yeah. Okay, so now again, so what do I need in order to make a monad? Well, I need a return which takes an x and goes into m of x. My m here is f composed with g, right? So I need a way to go from x to g of f of x, because that's how the composition works. And then I need a join which takes m of x and tells me gives me back an m of x, right? So joining two layers back into one layer, which is going to be slightly terrifying when we look at it here. It's going to go from g of f into g of f. So let's maybe worry about return first, because that one's usually the easier one, right? Okay, so I need to go from x to g of f of x. And I should use my adjunction somehow, right?
Yeah, but the adjunction is saying whenever you want a G on the right, it's enough to have an F on the left.
Yeah, so I can flip this G on the right, because G is the right adjoint, into an F on the left, right? I do 2 of the adjunction. That's saying that in order to get a G on the right, it's enough to have an F on the left. So if I do that to something, let's see what happens. So now I flip the G on the right to an F on the left. And so now I need to give something from f of x to f of x. Right? That's the one thing I know how to give in an arbitrary category, right? So this is the identity in D. Okay, and then I need to show that this is natural, but I know that this 2 function here is natural. So I prepared the proof of this. It's just using that fact twice. So these are the ones that specializes one of the 2 things to be an identity. Right? So that's that. I don't think that's very interesting. Okay, and then what about the join? Can we do the same trick? Well, not directly, right? Because now I don't have start and end. Well, I could move this G to an F here again. But then in the end, I would just have all of this that would need to go into f of x, right?
Yeah.
Okay, so that's an f. Yeah, okay, but so then I still have the same problem. I need to go from a g to an f.
Yeah.
But I could try something else, right? I actually have a g here and a g here. So I can use the functoriality of g. That's going to peel off
yeah.
1 g each. Okay, I can always try that. I'm not sure if it's going to work or not. And now here I have an f on the left that I could turn to a g on the right.
Yes. Now you notice we also have the option to use the functoriality of f, but then we'll be, if we did that, we'd be comprehensively screwed.
Right, because then we need to go from g of f into x, but we have
g's in the wrong place. So yeah, we got an f on the left, and if we flip it over,
flip it to the right to
then
a g,
it's looking very good indeed.
So that's flipping the g over to an f. get in the end. So now I'm again in a good situation where I need to go from one place to the same place, which is the one thing I can do. But this time in C. Right. So again, we see that we're kind of using all of the structure, more or less. We haven't used all of the laws yet, but we certainly used the to and the from. So I've used the naturality of to, and to show that this is natural is a little bit more involved. So rather than doing it step by step, I suggest we again just look at the interesting steps. And it's the fact that from is natural here. It looks very much like the proof up here, but now we have this g functor on top of it that the solver will take care for us. But okay, and then we should prove the laws that if we return and then join, that should be the identity. That again, I've already prepared. What is it using? It's just using naturality of to. And the fact that to and from cancel out here. Right. The other law is using that they cancel out the other way around. So left inverse of. And the final law
It's a bit more of a slog.
It's a bit of a slog. And there's nothing really interesting going on, right? It's just naturality of from. And the final laws here are, sorry, yeah, last steps. But again, we used exactly everything, right? We used naturality of to and from, and we used left inverse of and right inverse of. And that's a good sign that we can actually do what Jake suggested and say that we have some chance of every monad coming from an adjunction because we used all of the structure. If we didn't use all of the structure, then we could tweak that to make it not come from an adjunction, right? But to prove that is even more of a slog.
Yeah, it's also
we could. It was quite fun though, so we could maybe consider to do it next week. Again, yes. Skipping all of the
So
details.
It's also the case that we're noticing that an adjunction gives you a monad, but by composing the left adjoint and the right adjoint in whichever order is the one that works. And you can imagine that that there might be more than one adjunction for a given monad. That, essentially we're saying monads chop up into a left adjoint and a right adjoint, but they don't necessarily chop up uniquely. No. Every adjunction gives you a monad, and that's the only way you get monads.
Yeah.
But
there can be many different adjunctions that give you
the same monad.
In fact, there's a whole category of adjunctions. It's a whole category of adjunctions that give you a monad.
Yes.
And this has a terminal and an initial object. So there's a smallest one and the greatest one.
Is this terminal initial monad?
So here you say take some object in this category. And
you're doing it for base.
Yeah.
Yeah. Have we done?
So call it free-forgetful.
Yes.
Right. So that's a fun game to play. So do we still have that in this file? No, it's in the last week.
So there are lots of fun things to do here, actually.
So this, maybe we'll come back to this. But for example, is this a good example? It's not really a good example. I thought we had an example where, starting the previous week.
Is currying part of the homework?
No, it was part of homework 1, but with a less fancy name, of course.
Right. Because that's a beautiful example. Which I could sketch on the board while you're hunting. Might not end up on the video, but
Yeah, right.
yes.
So okay, so we didn't do the example I wanted, so maybe I'll just say it out loud. You have an adjunction between sets and pointed sets, where you add a point, which is left adjoint to the forgetful thing, which forgets about the point. So if you construct a monad out of this, you get a maybe monad, right, which takes a set and adds in a nothing. Yeah, but we did it directly as a monad on pre-orders. So that's why I also thought we did it. But yes, so if you wanted to do it that way, you would actually go from pre-orders to pre-orders with the bottom element, right? And then you forget about the fact you had a bottom element, and that gives you a new element.
But one of our favorite adjunctions is the one that says, if we're, should pull a colored pen out of my pocket.
Blue.
Yes. Well, I should keep them in order, I suppose. So a function from A to functions from S to B is the same as a function. It's the same stuff as functions from pairs of A's and S's to B. Right? Doesn't matter whether you take the A and the S one at a time or whether you take them as a pair. And then what does this turn into? It turns, when we compose these two operations, S into and times S, we get the thing that takes any X and maps it to S to X times S. Or that's to say something which starts with an S. So, so this takes a type of values and gives you a type of stateful computations that compute values.
The state monad is arising from the carry-uncarry adjunction.
And so that's one of many adjunctions that give you the state monad.
Okay.
I shouldn't steal the blue pen.
No, but we should stop here, I think.
Yes.
So hope you enjoyed, and see you next week.